Hey everybody, welcome to the Vapor Pressure of Water Lab lecture portion. Let's just go ahead and get right in. So, although the average kinetic energy of molecules of a liquid is a function of temperature, the exact amount of energy of a specific molecule is totally random. At given temperatures, the energies of molecules of a liquid are distributed about a mean value, with both very slow molecules and very fast molecules present. Now, because the number of the fast molecules is a function of temperature, the rate at which liquid molecules escape into the vapor phase is also a function of temperature. Now, within a gas phase in contact with a liquid phase, the molecules are moving randomly and are constantly colliding with each other and with the liquid phase. So slow-moving gas molecules mean losing sufficient energy to cause it to condense back into a liquid. The rate of reaction depends on the number of collisions. Rate is directly proportional to the partial pressure of the vapor, and there are two competing processes that are occurring. That's evaporation and condensation. Your stimulus or your heat causes the evaporation to start occurring faster, which means vapor pressure is going to increase. That works both ways. It's vice versa, okay? Either way, at a constant temperature, an equilibrium state will be reached where evaporation and condensation are going to be occurring at equal but opposite rates. Now, if temperature rises, more vapor is going to form. Your condensation increases until the equilibrium is reestablished at that new temperature, and vice versa with the exact same outcome. For now, let's just assume that water liquid and water gas are interchangeable. Okay, water liquid and water gas are interchangeable. That's what we're just going to assume right here. You have a Kp, and that's going to equal your equilibrium constant in terms of pressure. K for constant and P for pressure. Your pH 20 vapor, or your pH 20 vapor equals the pressure of water vapor above the liquid in a closed system, like a burette or something like that. In this particular experiment, you're going to use Gibbs free energy, which is a function of G. So delta G is your Gibbs free energy. Delta H is your enthalpy, which is energy. And delta S is going to be entropy, or your disorder. The little tiny degree sign means standard conditions, right? It's not really a degree sign, but that's how I'm relating it to you right now. This equation, or the formula, whatever you want to call it, shows the change in Gibbs free energy. You have to remember that all temperatures should be in Kelvin. Don't forget, you're going to have to convert your temperatures to Kelvin for this lab. Now, your KEQ is your equilibrium constant, and it relates to Gibbs free energy as shown here. Your capital R is your gas law constant. This is all going to be in your appendix also, but your gas law constant, 8.314 joules per mole Kelvin. And then your T is temperature. Now, for me to show you these, I'm just going to show you the first one. What we have here is everything that we're explaining to you. Your P is going to be pressure, T, temperature, your Ln, which is your natural log on your calculator, and you can actually get there through a series of steps. So that's where I'm going to take you at right now, okay? Now, you're going to solve equation A. You'll solve equation A. You're going to be given this information. You've got some constants. They're available to you in your appendix. You're going to look those up, and you're going to solve for your equation A. Then you're going to substitute the answer you have for the right side of A into B. Okay, the right side of A is going into B. Then you can take your answers from the previous step, plug it into C. And if you use algebra to rearrange the formula, don't forget to add the negative sign. Remember algebraic rules. Then you will come up with your LNP vapor. And this is going to be the actual formula for that. So let's just talk about that formula for a few minutes. Now, in this experiment, you're going to determine vapor pressure as a function of temperature, and you're going to plot the natural log of vapor pressure versus the inverse pressure in Kelvin. This should yield a linear best fit line that you can use to calculate change in temperature and change in entropy of water using this equation. Remember, your little triangle T is your change of temperature. Your triangle H is your change of temperature. Your little triangle of S is going to be your change in entropy. So look at this equation and determine what combination of variables are going to represent the slope and what combination of variables is going to represent the y-intercept if the natural log of vapor pressure is plotted on the y-axis and T is plotted on the x-axis. Now, again, just as I did before in freezing point depression, I don't normally do trivia when we're just doing a lecture on a video, but I just figure, why not give you an opportunity to earn some bonus points? You just need to create yourself a tab in your lab notebook, excuse me, call it bonus points, put the answers in there, no need to write them down and turn them in. I will look at them the next time I open your book to check your next lab notebook. So your first question, what is the formula to convert Celsius to Kelvin? What is the formula to convert Celsius to Kelvin? Number 2, what does the gas bubble in the graduated cylinder contain? Number 2, what does the gas bubble in your graduated cylinder contain? Number 3, what are you going to use to determine just the vapor pressure of water? What are you going to use to determine just the vapor pressure of water? Number 4, what does P total equal? What is your P total equal? And last but not least, how do you calculate P air? How do you calculate P air? All right, with that being said, that's it for the lecture. It's really short. If you have any questions, make sure you're reaching out to me via email. And I look forward to seeing you guys in class. Good luck.